Welcome. You have nowhere to be right now and nothing left to do. Let your body settle into wherever you are resting and allow your breath to slow and deepen. Tonight, we are going to drift together through one of the most serene and wonder-filled journeys the human mind has ever taken, a quiet voyage outward through the cosmos in search of a world like our own. Simply let the words wash over you and rest. Earth is the only confirmed planet known to harbor life. Of all the worlds we have ever found, touched, or turned our instruments toward, this one, the one beneath you right now, remains the single place in the universe where life is known to exist. Every ocean, every forest, every breath taken by every creature is part of something extraordinarily rare. There is something deeply settling in that thought. We are already home to the only confirmed miracle of its kind. The habitable zone is the range of orbital distances where liquid water can exist on a planet's surface. Astronomers sometimes call it the Goldilocks zone, not too hot, not too cold, but just right for water to remain a liquid rather than boiling away or freezing solid. It is a band of possibility that wraps around every star in the sky. Whether a planet falls within that band depends on how far it orbits and how brightly its star burns. Earth sits nestled comfortably within ours. Earth orbits the Sun at an average distance of about 150 million kilometers. That number is so large, it is hard to hold in the mind, so astronomers use it as a unit of measurement, all its own, one astronomical unit. It is the cosmic ruler against which all other planetary distances are measured. Light itself takes about 8 minutes to cross that distance. Every sunrise you have ever seen is the arrival of light that began its journey 8 minutes before you opened your eyes. The concept of a second Earth requires a rocky planet of similar size and mass to our own. Gas giants and ice giants, for all their grandeur, cannot offer a firm surface where oceans pool and continents rise. What we are searching for is something solid, a world with enough gravity to hold an atmosphere close, enough interior warmth to keep geology alive, and enough similarity to our own planet that the conditions for life as we understand it might take hold. A world, in other words, that feels familiar. Venus and Mars were once considered the most likely candidates for life in our solar system. For centuries, they were our nearest neighbors and our greatest hopes. Venus, shrouded in cloud, seemed to some like a warm, tropical world. Mars, with its reddish hue and polar ice caps, seemed to others like a cooling Earth. Early astronomers looked at them with longing and imagination. The truth, when we finally reached them, turned out to be far more complex and, in its own way, even more fascinating. Mars has the largest dust storms in the solar system, lasting months at a time. When conditions are right, a storm can begin in one small region and slowly expand until it wraps around the entire planet, blotting out the sun for weeks on end. The sky turns a deep, amber brown, and the surface disappears beneath a haze of fine red dust. These storms are not violent in the way a hurricane is violent. They move slowly, almost like a tide, a planet-wide exhale of rust-colored air drifting in near silence. Ancient Mars likely had liquid water flowing across its surface over 3 billion years ago. We can still read the evidence in the land itself: carved river valleys, ancient lake beds, and shorelines etched into rock by water that has long since vanished. For perhaps hundreds of millions of years, Mars was a wetter, warmer place. The light that once glinted off those ancient rivers left that world long before our earliest ancestors walked the Earth. What happened to all that water is one of the most quietly moving questions in planetary science. The Mars Curiosity rover discovered complex organic molecules in Martian rock in 2018. Organic molecules are the carbon-based building blocks from which life is constructed, and finding them preserved inside ancient rock was a remarkable moment. They do not confirm that life ever existed on Mars. They can also form through non-biological chemistry, but they tell us that the raw ingredients were present. Curiosity found them sealed inside mudstone, protected for billions of years, as if the planet had been quietly keeping a secret. Mars has a thin atmosphere composed mostly of carbon dioxide at about 0.6% of Earth's atmospheric pressure. Standing on the Martian surface, you would feel almost nothing. The air is so sparse, it would offer no more resistance than the near vacuum of a high-altitude balloon flight on Earth. It cannot shield the surface from radiation, and it cannot hold warmth the way our own sky does. And yet, it is still an atmosphere, still a thin, translucent veil wrapped around a world, drifting in the dark. Let yourself settle now. There is nowhere to be, nothing to hold on to, nothing left to figure out tonight. Feel the weight of your body softening into the surface beneath you, each breath arriving a little slower, a little easier than the one before. Let your thoughts drift like mist, not pushed away, just allowed to dissolve on their own. You are safe. You are still, and all you need to do is rest. The Perseverance rover collected rock core samples from Mars that may contain biosignatures. With a slender titanium tube, the rover carefully extracted cylinders of ancient Martian rock and sealed them away for a future mission to retrieve. These samples come from a dried lakebed called Jezero Crater, a place where water once pooled for perhaps millions of years. Scientists believe that if life ever stirred on early Mars, traces of it, chemical whispers preserved in stone, may be waiting inside those small sealed tubes. Venus has a surface temperature of about 465 degrees Celsius due to a runaway greenhouse effect. That is hot enough to melt lead, and it is the result of a thick blanket of carbon dioxide trapping the sun's heat with no way to escape. What makes Venus so striking is how familiar it once may have been, a rocky world, similar in size to Earth, perhaps even with ancient oceans long ago. Somehow, slowly, its climate tipped beyond any return, and the planet became the scorched, pressurized world it is today. Venus rotates so slowly that a day on Venus is longer than its year. It takes about 243 Earth days for Venus to complete a single rotation on its axis, but only about 225 Earth days to travel once around the Sun. This means a Venusian sunrise is an extraordinarily rare event. The Sun creeps across the sky with almost imperceptible slowness. And because Venus rotates in the opposite direction to most planets, that sun rises in the west and sets in the east, painting the sky in a direction that feels gently, quietly reversed. The Soviet Venera probes survived only about an hour on Venus's crushing surface before failing. These were among the most courageous machines ever built, engineered to withstand pressures 90 times greater than Earth's atmosphere and temperatures that could melt metal. They descended through thick clouds, touched down on volcanic plains, and sent back the first photographs ever taken from another planet's surface. Then, one by one, they fell silent. Their short lives told us more about Venus than centuries of observation from afar, and there is something quietly moving about how briefly they endured. Jupiter's moon Europa has a subsurface ocean estimated to contain twice as much water as all of Earth's oceans combined. Beneath a shell of fractured ice, a vast liquid ocean stretches around the entire moon, kept from freezing by the gravitational pull of Jupiter kneading Europa's interior and generating heat. The idea of a global ocean hidden under ice, orbiting a gas giant hundreds of millions of kilometers from the Sun, expands everything we thought we knew about where water, and perhaps life, can exist. That ocean has been quietly waiting there for billions of years. Europa's icy shell is estimated to be between 10 and 30 kilometers thick. It is a remarkable layer, ancient, fractured, and covered in a web of reddish-brown lines where the ice has cracked and refrozen over millions of years. Scientists study these patterns from afar the way a reader might trace lines in an old map, looking for clues about what moves beneath. The ice is both a barrier and a record, holding within its layers a long, slow history of tides and shifts driven by a hidden ocean below. The light reaching Europa from the distant sun is barely a glimmer, and yet beneath the ice, warmth persists. NASA's Europa Clipper mission, launched in 2024 to study the moon's potential habitability. The spacecraft will make nearly 50 close flybys of Europa, skimming through its thin exosphere and studying the ice, the ocean beneath, and the chemistry of its surface. It carries instruments designed to listen for signs of warmth, salt, and organic molecules, the quiet indicators that a place might be hospitable to life. Europa Clipper will not land, but it will listen closely, the way you might press your ear gently to a door, sensing what stirs on the other side. Saturn's moon Enceladus shoots geysers of water vapor and ice particles into space from its south pole. Near the southern tip of this small, brilliant moon, long fractures in the ice called tiger stripes release plumes that rise hundreds of kilometers above the surface and feed material into one of Saturn's rings. The geysers are driven by heat from within, tidal forces from Saturn, squeezing the moon's interior, keeping a liquid ocean from freezing solid. It is one of the most extraordinary sights in the solar system, a tiny moon, bright as a mirror, exhaling into the dark. The Cassini spacecraft flew directly through Enceladus's plumes and detected hydrogen and organic compounds. Rather than simply observing from a distance, Cassini dipped through the rising geysers and tasted them, its instruments analyzing the chemistry of what Enceladus was exhaling into space. It found hydrogen, which on Earth is produced by reactions between hot water and rock on the ocean floor, the same kind of chemistry that sustains life around hydrothermal vents. It found organic molecules, the carbon-bearing compounds that form the architecture of living things. Cassini told us, in the quietest possible way, that Enceladus has nearly everything life needs. Saturn's moon Titan has lakes and seas of liquid methane and ethane on its surface. Not water, but something else entirely. Hydrocarbons pooled in shallow basins near the poles, their surfaces smooth and dark, reflecting the hazy amber sky above. Titan's lakes are calm and still, fed by slow methane rains that fall through an atmosphere thicker than our own. It is a world of muted oranges and browns, draped in a permanent golden haze, where rivers of liquid methane carve channels through icy highlands and drain into quiet, mirror-still seas. Let your body settle a little deeper now. Feel the weight of your limbs releasing into the surface beneath you, heavy and unhurried. There is nothing to hold on to and nowhere to be. Let each breath come and go on its own, slow and even, like the tide moving in the dark. Your thoughts can drift, loose and unattached, like clouds moving across a quiet sky. You are safe and still and resting. Simply let yourself float. Titan is the only moon in the solar system with a dense atmosphere. Where most moons exist in near-airless silence, Titan is wrapped in a thick blanket of nitrogen laced with methane and complex organic haze, pressing down at a surface pressure slightly greater than Earth's own. Standing on Titan, you would need no pressure suit, only warmth and breathable air, which it does not provide. But the sky above would not be empty. It would be layered and amber, glowing softly, a world enclosed in its own slow weather. The Dragonfly mission is planned to send a rotorcraft lander to Titan in the 2030s. Rather than rolling across a surface, Dragonfly will fly, lifting off on twin sets of rotors, gliding through Titan's thick air from one landing site to the next, covering more ground than any rover has managed on another world. It will sample the surface chemistry, searching for organic molecules and the building blocks of life. The image is a quietly wonderful one, a small craft, buzzing gently through golden haze, exploring a distant moon, the way a dragonfly skims the surface of a pond. Jupiter's moon Ganymede is the largest moon in the solar system and has its own magnetic field. Larger than the planet Mercury, Ganymede is a world of ancient dark terrain and younger, grooved bright ice, its surface shaped by billions of years of geological activity. Deep within, a salty ocean is thought to lie between layers of ice, and unlike almost any other moon, Ganymede generates its own magnetic bubble, a miniature magnetosphere nested inside Jupiter's enormous one, a quiet, hidden force field surrounding a world of ice and rock. Callisto, another of Jupiter's moons, may also harbor a subsurface liquid water ocean. Callisto is the most heavily cratered object in the solar system, its ancient face marked by billions of years of impacts, unchanged and deeply still. Beneath that scarred surface, scientists believe a layer of salty liquid water may persist, kept from freezing by the faint warmth of tidal forces and the insulating weight of ice above. It is a world that looks entirely frozen and finished from the outside, yet may carry something fluid and alive within, a reminder that stillness on the surface does not always mean stillness below. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, but no planet-sized world. It is often imagined as a crowded, chaotic place, but in truth, the belt is mostly empty space. The rocky bodies within it spread so far apart that a spacecraft can pass through without ever coming close to a collision. Jupiter's immense gravity long ago prevented this material from gathering into a planet, leaving instead a scattered family of fragments, some the size of mountains, others no larger than a house, drifting in slow, wide orbits through the dark between two worlds. The dwarf planet Ceres in the asteroid belt has bright spots that are deposits of sodium carbonate. When the Dawn spacecraft first approached Ceres, mission scientists were puzzled by two intensely bright points of light shining from within a large crater. As Dawn drew closer, the picture resolved: brilliant white patches of sodium carbonate, a salt left behind as briny water from beneath the surface, slowly evaporated into space. Ceres, it turned out, is not merely a dry relic of the early solar system, it is a geologically active world, quietly exhaling salt into the dark. The light from those bright patches traveled across the void and reached our instruments like a soft signal, unexpected and serene. The Kuiper belt extends from Neptune's orbit to about 50 astronomical units from the Sun. Beyond the familiar planets, the solar system does not simply end, it opens into a wide, frozen ring of icy bodies, remnants from the earliest days of planetary formation. Pluto lives here, along with countless other dwarf planets and icy worldlets, all orbiting in a vast, slow procession around a sun that appears from this distance as little more than a very bright star. The Kuiper belt is a place of extraordinary stillness, where objects drift in orbits so wide that a single year there lasts hundreds of Earth years. Pluto has a heart-shaped nitrogen ice plain called Tombo Regio. When the New Horizons spacecraft swept past Pluto in 2015, one of the first and most striking features it revealed was an enormous pale plain shaped unmistakably like a heart stretching across the face of the small world. Named in honor of Clyde Tombaugh, the astronomer who discovered Pluto in 1930, this frozen expanse is made of nitrogen and carbon monoxide ice, smooth and bright against Pluto's darker, more rugged terrain. It is one of the most quietly poetic images the solar system has offered us, a distant, cold world wearing something that looks, from far away, like warmth. The New Horizons spacecraft revealed Pluto has a surprisingly complex and geologically active surface. When New Horizons made its historic flyby in 2015, scientists expected to find a simple, frozen, battered world, ancient and still. Instead, they discovered towering mountains of water ice, smooth plains reshaped by slow geological processes, and signs that Pluto's interior may still hold enough warmth to drive change across its surface. A world so small and so far from the Sun, quietly alive in its own unhurried way. The Oort cloud is a vast spherical shell of icy bodies extending up to 100,000 astronomical units from the Sun. This immense invisible envelope surrounds the entire solar system like a great hollow sphere, stretching nearly halfway to the nearest star. The icy bodies within it drift in extraordinary solitude, separated by distances so enormous that they may never come close to one another across billions of years. It is the outermost boundary of our Sun's gravitational family, a place of profound ancient stillness at the very edge of home. There is nothing you need to do right now, nowhere to be, nothing to hold on to. Let your body settle a little more deeply into the surface beneath you, and allow your breath to find its own slow, natural rhythm. Each exhale carries the last traces of the day away from you. The thoughts drifting through your mind need not be followed. Let them pass like distant lights moving softly through the dark. You are safe, you are still, and rest is already finding you. The nearest star system to Earth is Alpha Centauri, about 4.37 light-years away. Even traveling at the speed of light, the fastest anything in the universe can move, it would take more than 4 years to reach it. By any measure of human experience, that distance is almost beyond imagining. And yet, in the grand scale of the galaxy, Alpha Centauri is our closest neighbor, a familiar presence in the southern sky, burning steadily across the dark for anyone who takes a quiet moment to look up. Alpha Centauri is actually a triple star system, consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. What appears to the unaided eye as a single brilliant star is in truth 3 suns bound together by gravity. 2 of them, Alpha Centauri A and B, orbit each other in a slow, graceful dance over roughly 80 years. The third, Proxima Centauri, wanders much farther out, tracing an enormous orbit around the other 2 over immense stretches of time. 3 suns, 1 family, drifting together through the galaxy. Proxima Centauri is a red dwarf star and the single closest star to our Sun. It is small and cool by stellar standards, glowing with a deep reddish hue, rather than the brilliant white-yellow of our own Sun. If you could stand near it, its light would feel dim and ruddy, very different from the warm daylight we know. Yet Proxima Centauri is ancient and extraordinarily long-lived, burning its fuel so slowly and carefully that it will continue to shine for hundreds of billions of years, long after our own Sun has faded. Proxima Centauri b is an exoplanet orbiting in the habitable zone of Proxima Centauri. Discovered in 2016, this world orbits its star at a fraction of the distance Mercury orbits our Sun, completing a full year in just over 11 Earth days. Because Proxima Centauri is so much cooler and dimmer than our Sun, that close distance still places the planet within the range where liquid water could, in principle, exist on its surface. It is the closest known exoplanet to Earth, a world that, in cosmic terms, is practically next door. The light from that small red star has been falling on that planet's surface for billions of years. Proxima Centauri b receives far more ultraviolet and X-ray radiation than Earth does due to frequent stellar flares from its host star. Red dwarfs like Proxima Centauri are prone to powerful eruptions that release intense bursts of high-energy radiation. For a planet orbiting so close, these flares could be a significant challenge for any life attempting to take hold on the surface. Scientists believe that a strong magnetic field or a thick atmosphere might offer some shelter. Whether Proxima Centauri b has either of those remains one of the many open, unhurried questions we are slowly learning to ask. Red dwarf stars make up about 70% of all stars in the Milky Way galaxy. They are by far the most numerous type of star in existence, filling the galaxy in their billions, most of them too faint to see with the unaided eye. The stars we notice in the night sky, the bright familiar ones, represent only a small fraction of what is actually out there. The vast majority of the galaxy's stars are these small, cool, unhurried suns, burning low and steady in the dark. In a very real sense, the galaxy belongs to red dwarfs. Red dwarf stars can live for trillions of years, far outlasting sun-like stars. Our own sun will burn for roughly 10 billion years in total, a span of time almost impossible to hold in the mind. But a red dwarf, burning its fuel with extraordinary frugality, can shine steadily for 1 trillion years or more. The universe itself is only about 13.8 billion years old, which means no red dwarf has yet had time to die naturally. Every red dwarf that has ever formed is still burning somewhere out there, patient and enduring, older than almost anything else we can imagine. Planets orbiting red dwarfs are often tidally locked, keeping one face permanently turned toward their star. Just as our moon always shows the same face to Earth, these worlds are held in place by the steady gravitational pull of their sun. One hemisphere basks in perpetual daylight, warm and lit for billions of years without pause. The other rests in endless night, cool and still beneath an unbroken dark. Between them, along the boundary where day meets night, a narrow twilight band stretches around the planet, a place of long amber dusk that never quite becomes day and never quite becomes night. The TRAPPIST, one system, contains 7 Earth-sized planets orbiting an ultra-cool red dwarf star. 7 worlds, all of them roughly the size of our own, circling a single small star in a kind of quiet, unhurried procession. The star they orbit is so cool and dim that it glows a deep, muted red, barely a star at all by some measures, and yet enough to hold 7 planets in its embrace. Announced to the world in 2017, this discovery felt like something out of a long, slow dream. 7 chances, all gathered close together, all waiting to be understood. 3 of the TRAPPIST, 1 planets orbit within the system's habitable zone, the range of distances where liquid water could rest on a planetary surface. 3 worlds, side by side in the same temperate band, each one a candidate for something more. Scientists believe at least some of them could have water, and perhaps the right conditions for chemistry to grow complex and slow. The thought of 3 potentially habitable worlds in a single star system is one of the most quietly astonishing things modern astronomy has given us. We have not yet looked closely enough to know, but we are looking. Let yourself settle a little more deeply now. There is nothing to hold on to, nothing to solve or remember. Let your shoulders drop. Let your hands rest open and still. Each breath is slower and quieter than the last, in through the nose and out, long and easy. The facts and the distances and the stars can drift now, loosening gently like the last thoughts before sleep. You are here, warm and safe, and the universe is vast and unhurried around you. There is nowhere to go. There is nothing to do. Only rest, drifting softly, like starlight crossing the dark. TRAPPIST. 1 is located about 39 light-years from Earth, nestled in the constellation Aquarius. 39 light-years is an almost incomprehensible distance by any human measure, and yet, in the scale of the galaxy, it is extraordinarily close. Aquarius is a familiar constellation. Visible from much of the world on clear autumn nights, its stars scattered across the southern sky in a loose, unhurried pattern. Somewhere within that constellation, invisible to the unaided eye, a small red star holds 7 worlds in its quiet orbit. The light reaching us from that star tonight left its surface 39 years ago. The TRAPPIST-1 planets were discovered primarily through the transit method of planet detection. Astronomers watch the light from that small red star with extraordinary patience night after night, looking for the faintest, most fleeting dimming, the shadow of a world passing across its face. Each planet, in its orbit, eventually crossed between us and its star, leaving a tiny trace in the data. 7 planets, each one announced by a whisper of diminished light. It is a method built entirely on stillness and attention, on the willingness to wait and watch without rushing toward an answer. The transit method detects exoplanets by measuring the tiny dimming of a star as a planet passes in front of it. When a planet crosses between its star and our telescopes, it blocks a small fraction of the starlight, sometimes less than 1% of the total brightness. Astronomers measured that dip with extraordinary precision, recording how deep it is and how long it lasts. From those two quiet numbers, they can calculate the planet's size, its orbital period, and its distance from its star. It is a remarkably delicate technique, finding whole worlds by the faintest, most momentary shadow. The radial velocity method detects exoplanets by measuring the wobble a planet induces in its host star. A planet does not simply orbit its star. Both the planet and the star orbit their shared center of mass, so the star itself moves in a small, slow circle. As the star moves toward us, its light shifts very slightly toward the blue end of the spectrum. As it moves away, it shifts toward the red. By measuring those tiny color shifts with great care, astronomers can infer the presence of an unseen world tugging gently at its sun. It is, in its way, like hearing a heartbeat through a wall. The first confirmed detection of an exoplanet around a sun-like star was 51 Pegasi b, announced in 1995. For most of human history, the question of whether other stars harbored planets was entirely unanswerable, a matter for philosophy, not science. Then, in a single year, everything changed. Two astronomers measured the faint wobble of a star in the constellation Pegasus and found, unmistakably, a planet. The discovery opened a door that has never been closed. From that one world, we have gone on to find thousands upon thousands of others, each one a reminder that the universe is far more full of planets than we ever dared imagine. 51 Pegasi b is a hot Jupiter, a gas giant orbiting extraordinarily close to its host star. It completes a full orbit in just over 4 Earth days, skimming so near to its sun that its surface temperatures reach hundreds of degrees. Before this discovery, astronomers had assumed that giant planets could only form in the cold outer regions of a solar system, far from their stars. Finding one so close, so hot, so unlike anything in our own neighborhood, quietly overturned decades of thinking. The universe, it seemed, was far more inventive than our models had allowed. It was a reminder to hold our assumptions loosely. Michel Mayor and Didier Queloz won the 2019 Nobel Prize in Physics for discovering 51 Pegasi b. The Nobel Committee recognized their work as one of the most transformative moments in the history of astronomy. Two scientists, working with careful patience at an observatory in southern France, had changed the way humanity understood its place in the cosmos. Their prize was awarded nearly 24 years after the discovery itself, a quiet acknowledgement that some revelations take time to fully settle into the world. The universe had spoken, and two people had been listening closely enough to hear it. The first exoplanets ever confirmed were discovered orbiting a pulsar, announced in 1992. This was a deeply unexpected place to find worlds. A pulsar is the collapsed remnant of a massive star that has ended its life in a tremendous explosion, not the kind of place astronomers had imagined planets could survive. And yet, there they were, circling a dead star in the darkness. The discovery arrived quietly, almost gently, before the broader world was ready to think about exoplanets at all. It was a reminder that the universe rarely waits for our expectations to catch up with it. Astronomers Alexander Wolszczan and Dale Frail discovered those first pulsar planets around a neutron star known simply as a rapidly spinning remnant in the constellation Virgo. Wolszczan, working at the Arecibo Observatory in Puerto Rico, detected the almost impossibly regular pulses of the dead star and noticed tiny variations in their timing. Those variations, he realized, were caused by the gravitational pull of orbiting worlds. Frail helped confirm the finding. Together, They had found planets in the most unlikely of addresses, orbiting a stellar corpse, bathed not in warm sunlight but in radiation, silent and strange and real. The Kepler Space Telescope, launched in 2009 and discovered over 2,600 confirmed exoplanets. It was sent into an orbit around the Sun, trailing quietly behind Earth, and it spent years staring at the same region of sky without blinking. Kepler did not look for drama. It simply watched and waited and recorded the light of hundreds of thousands of stars with extraordinary steadiness. World after world emerged from its data, each one a small, certain answer to a question humanity had carried for centuries. No single instrument has done more to reveal how planet-filled our galaxy truly is. There is nothing you need to hold on to right now. Let your thoughts drift the way clouds move across a night sky, slowly, without direction, dissolving at the edges. Feel the weight of your body settling, each breath a little slower than the last. You are resting in a universe full of quiet wonders, and none of them require anything from you tonight. Simply let yourself be still. Let the darkness around you be soft and wide and safe. You are exactly where you are meant to be, and sleep is already finding its way to you. Kepler stared continuously at a single patch of sky containing about 150,000 stars. That patch of sky sat in the constellations, Cygnus and Lyra, a region chosen because it offered a rich, dense field of stars while remaining visible to the telescope year-round. Night after night, year after year, Kepler watched those stars without turning away. The light from each one was measured, recorded, and compared. In that patient, unwavering attention, Kepler found something extraordinary, that the sky was not empty between the stars, but filled, quietly and abundantly, with worlds. The Kepler mission revealed that most stars in the galaxy likely host at least one planet. Before Kepler, this was a hope, a reasonable guess, but not a certainty. After years of data, the numbers became clear. Planets are not rare exceptions scattered sparsely across the cosmos. They are the rule. Nearly every star you see on a clear night is almost certainly accompanied by at least one world of its own. The sky, which once seemed to hold only distant, unreachable fires, turns out to be a vast and populated place. That thought, held lightly in the mind before sleep, is one of the most comforting in all of science. Kepler discovered that small rocky planets are far more common than giant gas planets. Before this mission, astronomers had found many hot Jupiters and large gas worlds, partly because those were the easiest to detect. But when Kepler looked deeper and longer, a different picture emerged. Smaller planets, compact, solid, closer in size to Earth, turned out to outnumber their larger cousins by a wide margin. The galaxy is not dominated by giants. It is, instead, filled with modest, terrestrial worlds, rocky and quiet, orbiting their stars in the dark. The universe, it seems, has a preference for the small. The Kepler telescope ran out of fuel and was retired in 2018 after 9 years of operation. The mission had lasted far longer than its original 3.5-year design. When the last reserves of fuel were finally exhausted, mission controllers sent a final set of commands and placed the spacecraft into a safe, permanent orbit around the Sun. Kepler would not return. It drifts there still, trailing behind Earth, silent now, carrying within its memory the measurements of over 500,000 stars. It gave everything it had. The light it gathered will be studied for decades to come. The K2 mission extended Kepler's science by observing different fields along the ecliptic plane. After a mechanical failure left Kepler unable to hold its original pointing direction, engineers found a creative solution. They used the pressure of sunlight itself to help stabilize the telescope. By pointing along the plane of Earth's orbit around the Sun, Kepler could maintain its balance and continue working. The mission observed dozens of new star fields, studying a far broader range of stars and planetary systems than before. What could have been an ending became a second chapter, a quiet demonstration of how much can still be found when we adapt and continue. The TESS satellite launched in 2018 and surveys nearly the entire sky for transiting exoplanets. Where Kepler watched one small patch of sky, TESS turned its eyes outward in all directions, sweeping across the heavens in broad, overlapping arcs. Its 4 cameras divide the sky into sectors, dwelling on each one long enough to catch the faint, rhythmic dimming of a star as a planet crosses before it. TESS worked methodically, unhurried, covering the whole celestial sphere over the course of its mission. It is, in a sense, a great slow blink, patient, thorough, and quietly gathering the addresses of worlds. TESS has identified thousands of exoplanet candidates orbiting stars much closer to Earth than Kepler's targets. This closeness matters enormously. Nearby stars are brighter in our sky, which means their planets are far easier to study in detail with follow-up observations. Kepler mapped a distant neighborhood. TESS is mapping our own. Many of the world's TESS has flagged orbit stars visible to the naked eye on a clear night. It is a humbling thought that some of those steady, familiar points of light overhead may carry planets circling them right now, unhurried and unknown, waiting to be understood. The James Webb Space Telescope launched on December 25, 2021, and can analyze exoplanet atmospheres. It folded itself carefully into a rocket and rose into the sky on a winter morning, unfolding over the following weeks into a structure of extraordinary delicacy, a golden mirror 18 meters across, shaded by a sunshield the size of a tennis court. Webb settled into an orbit far beyond the Moon, where temperatures dropped low enough for its infrared detectors to work with breathtaking sensitivity. It was built, in part, to do something no telescope had done so well before, to read the air of other worlds. The James Webb Space Telescope uses transmission spectroscopy to detect the chemical fingerprints of gases in exoplanet atmospheres. When a planet passes in front of its star, a thin sliver of starlight grazes the very edge of the planet's atmosphere. Different gases absorb different wavelengths of that light, each leaving its own distinctive mark. Webb's instruments spread that filtered light into a spectrum and read those marks like a kind of language, one written in absorption lines and molecular signatures. Carbon dioxide, water vapor, methane, each leaves a trace as delicate and unmistakable as a fingerprint pressed lightly into the light. The James Webb Space Telescope detected carbon dioxide in the atmosphere of the hot gas giant known as WASP-39b in 2022. It was the first clear, unambiguous detection of carbon dioxide in the atmosphere of any world beyond our solar system. Carbon dioxide had been suspected in other atmospheres before, but never seen so cleanly and with such certainty. The announcement was quiet by the standards of the wider world, but within astronomy it carried the weight of a door swinging open. If Webb could read carbon dioxide in a distant giant, it could, in time, read the far subtler signatures of smaller, cooler, more Earth-like worlds. Let yourself settle a little more deeply now. There is nothing you need to hold on to. The day has already finished its work, and you have finished yours. Let your shoulders drop. Let the weight of your body press gently and completely into the surface beneath you. Each breath arrives on its own, without any effort from you. Each breath departs just as easily. You are resting in a universe full of quiet worlds, worlds orbiting in darkness, worlds wrapped in mist and cloud, worlds that have never known a single waking thought. And here, among all of them, you are simply still, simply breathing, simply here. The James Webb Space Telescope observed the TRAPPIST-1 planets and found that TRAPPIST, 1c likely lacks a thick Venus-like atmosphere. This was a meaningful result, and a sobering one. TRAPPIST. 1c sits in a region where, under the right conditions, a dense atmosphere might have persisted, but Webb's measurements suggested the planet's dayside is too warm for a substantial blanket of carbon dioxide to be present. It may be a bare, rocky world, its surface exposed directly to its star. The finding does not close the door on the system's other planets. It simply reminds us that even neighboring worlds can take very different paths. An exoplanet's atmosphere can be studied when starlight filters through it during a transit event. The technique relies on a brief and delicate moment. The planet is crossing the face of its star, and a razor-thin arc of its atmosphere is backlit by that stellar glow. Light passing through the atmosphere interacts with whatever gases are present, and those interactions leave their marks in the spectrum that reaches our telescopes. It is a method of extraordinary subtlety, reading the chemistry of a world tens of light years away from the faintest traces left in borrowed light. The universe, patient and generous, offers these clues to those willing to look carefully enough. Direct imaging of exoplanets requires blocking out the overwhelming glare of the host star. A star outshines its nearby planets by factors that are almost impossible to hold in the mind, 1 billion times brighter in visible light. In some cases, trying to photograph a planet beside its star is something like trying to photograph a firefly hovering next to a lighthouse from many kilometers away. The firefly is there, but the lighthouse drowns it completely. To see the firefly, you must find a way to cover the lighthouse, to extinguish that brilliant flooding light without disturbing the faint glow beside it. The coronagraph is a device used in telescopes to block starlight and reveal nearby planets. It works by placing a precisely shaped mask within the optical path of the telescope, intercepting the star's light before it can flood the detector. The idea traces back to a solar astronomer named Bernard Liot, who in 1930 invented a coronagraph to study the sun's faint outer atmosphere by blocking the solar disk itself. The same principle, refined over decades and made extraordinarily precise, now allows astronomers to suppress starlight well enough to glimpse the dim reflected glow of orbiting worlds. A small mask, held in exactly the right place, opens a window onto other Earths. The star system known as HAR 8799 was the first multi-planet system to be directly imaged, with 4 giant worlds captured in photographs taken in 2008 and 2010. Each planet appears as a faint point of light, orbiting a young bright star about 130 light-years away. The images required some of the most advanced telescopes on Earth, working at the very edge of what was then technically possible. To hold those 4 small dots of light in your mind is to understand something profound, that other solar systems with their own arrangements of worlds are not merely inferred but seen. They exist out there, turning slowly in their orbits, real and present. Beta Pictoris b was among the very first exoplanets to be directly imaged, and it orbits a young star wrapped in a broad, luminous disk of dust and debris. The disk itself is enormous, a swirling, flat ring of material left over from the formation of planets, catching starlight and glowing with a soft, diffuse radiance. Beta Pictoris b moves through this disk, like a traveler crossing a slow river of ancient dust. The star is thought to be only about 20 million years old, meaning astronomers are watching a solar system still in the early stages of becoming itself. It is a glimpse of our own distant past, a young world still finding its place. The super-Earth category describes rocky planets with masses ranging from 1 to 10 times the mass of our own world. They are not Earth scaled up in a simple way. Their greater mass may mean thicker atmospheres, stronger gravity pulling at the surface, and interiors under pressures we have never directly experienced. Some may be entirely wrapped in oceans, thousands of kilometers deep. Others may have surfaces of compressed rock, unlike anything in our solar system. The name is a convenience, a way of grouping worlds that share a rough family resemblance with our home, while remaining genuinely, fascinatingly different in character. Super-Earths are the most common type of planet found anywhere in the galaxy. Wherever astronomers have looked, around red dwarfs, around sun-like stars, across the spiral arms of the Milky Way, these mid-sized rocky worlds appear again and again in the data. Our own solar system, curiously, has none. There is nothing between the size of Earth and the much larger Neptune in our neighborhood, which makes us something of an outlier. The universe seems to favor building worlds somewhat larger than ours, filling galaxy after galaxy with planets that sit in a size range we have never had the chance to visit. They are the most ordinary kind of world, and yet to us entirely unknown. A well-studied world called J1214b is a super-Earth whose atmosphere has intrigued astronomers for years. Observations suggest it carries either a thick envelope of water vapor or a hydrogen-rich shroud, and distinguishing between the two has proven remarkably difficult. The planet orbits a small red dwarf star about 40 light-years away, completing each orbit in just over 38 hours. Its atmosphere appears featureless in the data, which itself is a clue. A flat, featureless spectrum often points to high clouds or haze blanketing the lower layers. Somewhere beneath that veil, a world waits, its true nature still folded quietly out of reach. The mini-Neptune category describes planets a little larger than Earth, but noticeably smaller than Neptune, wrapped in thick, voluminous atmospheres of hydrogen, helium, and heavier gases. They occupy a curious middle ground, too large and gassy to be rocky worlds in the familiar sense, yet far more compact than the great ice giants of our own solar system. Their interiors may contain deep layers of high-pressure water, or exotic ices compressed into forms that have no name in ordinary experience. Mini-Neptunes are among the most frequently detected planets in the galaxy, quietly abundant, drifting in their orbits around countless stars, their dense atmospheres holding their secrets with unhurried patience. There is nothing you need to do right now, nowhere to be, nothing to solve or remember or prepare for. Let your body settle a little more deeply into wherever you are resting. Notice the weight of your limbs, the easy rise and fall of your breath. Let each exhale carry away whatever the day left behind. You are held and still and safe. The mind can soften now, like a sky releasing the last of its light at the end of a long, unhurried evening. Let the thoughts thin and drift. Let the quiet deepen around you. You are already on your way toward sleep. Astronomers have noticed a curious absence in the population of known planets, a gap in sizes between about 1.5 and 2 Earth radii, sometimes called the radius gap or the Fulton gap. Planets tend to be found either smaller than this range or larger, but rarely within it. The leading explanation involves photoevaporation. Intense radiation from a young star can strip away the atmospheres of mid-sized worlds, pushing them into one category or the other. It is a natural sorting process driven by starlight over millions of years. The gap is a quiet signature of how planetary systems evolve, a space in the data that tells a story about transformation and loss. A rocky super-Earth known as Elias 1140b orbits within the habitable zone of a red dwarf star about 49 light-years from our own Sun. It is one of the more promising nearby candidates for a world that might support liquid water on its surface. The star it orbits is unusually quiet for a red dwarf, less prone to the violent flares that can scour nearby planets. Elias 1140b is somewhat larger and more massive than Earth, suggesting it may have retained a meaningful atmosphere over the long span of its existence. Astronomers have begun studying it with the James Webb Space Telescope, turning their most sensitive instruments toward this small, distant possibility. A planet called K2-18b sits in the habitable zone of its star and has drawn extraordinary attention for what Webb's instruments found woven into its atmosphere, signatures of carbon dioxide and methane, both present together. The planet is a sub-Neptune, larger than Earth and wrapped in a substantial gaseous envelope, and it orbits a cool red dwarf about 120 light-years away. The combination of carbon dioxide and methane in an atmosphere is notable because, under the right conditions, it can point toward processes we associate with living chemistry. The light that carries these molecular fingerprints left that world long before any of us were born, and it has arrived quietly with something worth listening to. In 2023, astronomers tentatively detected a possible signal of dimethyl sulfide in the atmosphere of K2-18b. The detection was not definitive. Scientists were careful to describe it as a hint, a whisper in the data, rather than a confirmed finding. Dimethyl sulfide is a molecule with a very specific story on our own world, and its possible presence in a distant atmosphere set the scientific community into a state of quiet, measured wonder. The James Webb Space Telescope gathered that faint molecular signature across 120 light-years of open space, folding it gently into the light it collected. On Earth, dimethyl sulfide is produced exclusively by living organisms, primarily marine phytoplankton, tiny ocean-dwelling life forms that release it as a byproduct of their biological processes. No known geological or purely chemical process on our world generates it in meaningful amounts. This makes it a potential biosignature gas, a molecule whose presence in another world's atmosphere could whisper of biology at work. The oceans of Earth breathe this compound into our skies in vast, invisible quantities each year. It is, in a sense, the breath of the sea, and the thought that a distant world might exhale something similar is one of the most quietly astonishing possibilities in all of modern science. A biosignature is any chemical, physical, or structural feature that provides evidence of past or present life. The definition is broad by design because life is inventive and varied, and scientists do not wish to overlook it by looking too narrowly. A biosignature might be a gas like oxygen or methane, a pigment that absorbs light in a particular way, or even the organized patterns of a living surface viewed from afar. On Earth, our entire biosphere has left its mark on the atmosphere, the rocks, and the chemistry of the oceans. Any world touched by life, scientists believe, would carry similar traces, signatures written into its very substance, waiting to be read. Oxygen and methane together in a planet's atmosphere would be a particularly compelling biosignature, because the two gases react with each other and destroy one another over relatively short timescales. If both were found present at the same time, something would have to be actively replenishing them, and on Earth, that something is life. Methane is exhaled by microbes and animals. Oxygen is released by photosynthesis. Their coexistence is chemically unstable, which means their simultaneous presence points toward a dynamic, living source. It is a kind of chemical tension that only biology seems able to sustain, a balance held in place by the quiet, ceaseless work of living things. The presence of ozone in an atmosphere is considered an indirect biosignature for oxygen. Ozone forms when ultraviolet light from a star breaks apart oxygen molecules, allowing individual oxygen atoms to recombine into 3-atom clusters. Because ozone is derived from oxygen, and because oxygen in large quantities on a rocky planet is strongly associated with life, detecting ozone in a distant atmosphere is a meaningful clue. Ozone also absorbs ultraviolet radiation powerfully, making it detectable even when oxygen itself might be harder to measure directly. Earth's own ozone layer is, in this sense, a quiet advertisement of the life thriving below it, a signal broadcast into space by every living breath our world has ever taken. When water vapor is detected in an exoplanet's atmosphere, it is treated as a meaningful indicator of that world's potential to harbor life as we know it. Water is the solvent in which all of Earth's chemistry of life takes place, and its presence in a gaseous form around a distant planet suggests it may exist in liquid form on or beneath the surface. Detecting water vapor requires the careful analysis of starlight filtered through a planet's atmospheric layers during a transit, a process of extraordinary delicacy. Several exoplanets have now shown water vapor signatures in their spectra. Each one is a small, luminous data point in the long, unhurried search for a world that might be something like our own. The boundaries of a star's habitable zone are not fixed. They shift depending on how luminous the star is and what kind of star it happens to be. A bright, massive star pushes its habitable zone far outward, while a dim red dwarf draws it in close. The color and temperature of a star also affect how its light interacts with a planet's atmosphere and surface. A world orbiting a cooler star might need to be much nearer to receive enough warmth, while a planet around a hotter star must keep its distance to avoid being scorched. The habitable zone is less a precise ring and more a broad, probabilistic region, a zone of possibility rather than a guarantee, shaped by the particular character of each star it surrounds. Let yourself settle now, just a little more deeply. There is nothing left to hold on to. Let your shoulders release. Let your jaw soften. Let the weight of your body be carried completely by whatever lies beneath you. Your breath is slow and even, moving in and out without any effort at all. The mind can let its last thoughts thin away, like mist dissolving in the early morning. You are drifting, unhurried, into the deep and restoring quiet of sleep. All the wonders of the universe will still be there, patient and vast, when you wake. For now, there is only stillness and warmth and rest. Whether a planet truly qualifies as habitable depends on far more than its distance from its star. Atmospheric pressure plays a crucial role. Too thin an atmosphere and liquid water evaporates away. Too dense, and the surface may be crushed under heat and weight. The chemical makeup of the atmosphere matters enormously as well, determining how much warmth is retained and whether the right molecules are present for complex chemistry. Geological activity, the slow churning of a planet's interior, replenishes gases, recycles minerals, and maintains the conditions that life requires over immense spans of time. Habitability is not a single threshold, but a web of interlocking conditions, each one quietly necessary. Plate tectonics on Earth plays a remarkable role in keeping our world's climate stable across vast stretches of time. As tectonic plates shift and subduct, carbon dioxide that has been locked into seafloor rocks is carried down into the mantle and eventually released back into the atmosphere through volcanic activity. This slow geological breathing, cycling carbon in and out of the air over millions of years, acts as a natural thermostat, preventing the planet from drifting too far toward freezing cold or scorching heat. Without this deep, unhurried recycling, Earth's climate might have wandered beyond the range where life could persist. The ground beneath our feet is, in its own slow way, one of the reasons we are here. Whether plate tectonics is common on other rocky planets remains an open and genuinely debated question among planetary scientists. On Earth, the crust is broken into great interlocking pieces that drift and grind across the surface over millions of years. But this behavior may not arise naturally on every rocky world. Some planets may have thick, immobile crusts that seal their interiors away from the surface entirely. Others might experience a different kind of geological expression, slow upwellings, volcanic resurfacing, or quiet interior convection that never quite breaks through. The answer, when it finally comes, will tell us something profound about how many worlds out there can truly sustain a long and stable climate. A planet's magnetic field can act as an invisible shield, protecting its atmosphere from being gradually stripped away by the relentless flow of charged particles streaming outward from its star. This stellar wind, invisible but persistent, can erode an unprotected atmosphere over millions of years, thinning it until little remains. A strong magnetic field deflects those particles, wrapping the planet in a vast and silent cocoon of protection. Without such a shield, even a world sitting comfortably within the habitable zone might slowly lose the very air that makes surface life possible. The magnetic field is, in a quiet way, one of a planet's most essential companions. Earth's magnetic field arises from deep within the planet, generated by the slow and powerful churning of molten iron in the outer core. As the liquid iron circulates, driven by heat rising from the inner core and the planet's rotation, it produces vast electrical currents, and those currents in turn create a magnetic field that extends far out into space. This process, called a magnetic dynamo, has been running for billions of years, quietly and continuously. The warmth at the center of our world, inherited from its formation and from the slow decay of radioactive elements, is ultimately what keeps the field alive. The invisible protection surrounding us today is a gift from deep within the Earth itself. Mars lost most of its magnetic field about 4 billion years ago, and this loss likely set the planet on a long, slow path toward the thin and arid world we see today. Without a protective magnetic field, the solar wind gradually peeled away the Martian atmosphere over vast stretches of time, leaving behind only a faint wisp of carbon dioxide. The surface, once perhaps warmed by a denser sky and touched by flowing water, grew cold and exposed. Scientists can still detect traces of ancient magnetism frozen into Martian rocks, like echoes of a field that once existed but faded away long before life on Earth had learned to walk on land. The size of a planet's iron core plays a significant role in determining whether it can sustain a long-lived magnetic dynamo. A larger core retains more heat from the planet's formation and contains more material to drive the convective currents that generate a magnetic field. A smaller or solidified core may cool too quickly, allowing the dynamo to weaken and eventually fall still. This means that two planets of similar size could have very different magnetic histories depending on how their interiors formed and evolved. When scientists search for habitable worlds, the invisible architecture deep inside a planet, the size and state of its core, matters just as much as what lies on its surface. When astronomers announced the discovery of Kepler 452b in 2015, they described it warmly as Earth's closest known cousin. It is a rocky planet orbiting within the habitable zone of a star, very similar to our own Sun, at roughly the right distance to allow liquid water on its surface. Its radius is about 60% larger than Earth's, making it a super-Earth rather than a true twin, but the resemblance was striking enough to capture the imagination of the world. Here, at last, was a world that seemed to rhyme with our own, a familiar shape in an unfamiliar corner of the galaxy, sitting quietly in the warmth of a sun-like star. The star Kepler 452 is about 1.5 billion years older than our own Sun, which means any life on its orbiting planet would have had considerably more time to take root and develop. 1.5 billion years is an almost incomprehensible span, longer than the entire history of complex multicellular life on Earth. In that extra time, whatever chemistry might have begun on such a world could have had the opportunity to grow, diversify, and reach toward complexity. We do not know whether life ever stirred there, but the thought lingers softly that somewhere in the direction of the constellation Cygnus, an older and quieter version of our story may have already been written. Tau Ceti is a nearby sun-like star, lying about 12 light-years from Earth, close enough to feel almost neighborly on the scale of the galaxy. It shines with a warm, steady light and has long attracted the attention of astronomers searching for worlds that might resemble our own. Evidence suggests it hosts multiple planets, some of which may fall within or near the habitable zone. Tau Ceti is slightly smaller and dimmer than the Sun, and it is notably older, giving any worlds around it an extended history. On a clear night, it is visible to the unaided eye in the constellation Cetus, a small, steady point of light that carries within it the possibility of other worlds. Let your body rest now, completely and without effort. Feel the weight of your limbs settle fully, as though the ground beneath you is holding you with great care. There is no need to follow any thought or hold any image in mind. Your breath moves on its own, slow and even, carrying you gently deeper with each exhale. The wonders of distant stars and ancient worlds can drift away now, like the last colors of a sunset fading softly into the dark. You are safe and still and unhurried. Let sleep come the way evening comes, gradually, without announcement, wrapping everything in its quiet and restoring dark. The star 61 Virginis is remarkably similar to our own Sun, nearly the same size, the same temperature, and the same warm golden color, and it lies just under 28 light-years away. Astronomers have found at least 3 planets orbiting it, all of them in the super-Earth mass range, circling their star in relatively close, swift orbits. While these particular worlds may orbit too near their star to be temperate, the system demonstrates that Sun-like stars readily form rocky planets. 61 Virginis is visible to the naked eye on a clear night, a quiet and familiar-looking star in the constellation Virgo, carrying its family of worlds in steady, unhurried silence. Barnard's star, the second nearest star system to our own, became the subject of quiet excitement in 2018 when astronomers announced a candidate planet orbiting it. The signal, detected through the radial velocity method, suggested a cold, rocky world circling just beyond the star's habitable zone. Subsequent observations cast doubt on the finding, and the scientific community remains cautious, classifying it as disputed rather than confirmed. Barnard's star is a dim red dwarf, ancient and unhurried, drifting slowly across our sky, the fastest-moving star visible from Earth. Whether or not a planet truly accompanies it, the star itself is a patient, enduring presence in the darkness, just 6 light-years away. Epsilon Eridani is one of the nearest Sun-like stars to Earth, lying just over 10 light-years away, and it has long held a special place in the imagination of astronomers. It is younger than our Sun, still surrounded by a broad, sweeping ring of dust and debris, the kind of disk that hints at planetary formation either underway or recently completed. Evidence suggests at least one planet may orbit within the system, though its precise nature remains under study. The star shines with a warm, slightly orange hue, visible to the unaided eye in the constellation Eridanus on a clear winter evening. It is close enough to feel intimate, a young and still-forming stellar family resting just at the edge of our cosmic neighborhood. Gliese 667c is a red dwarf star nestled within a triple star system, and what makes it remarkable is the crowded hospitality of its habitable zone. Astronomers have identified multiple planets orbiting this single small star, with several of them falling within or very near the region where liquid water could exist on a rocky surface. The 2 companion stars, Gliese 6067a and b, glow distantly in the sky of these worlds, painting their skies with a second and third sun. The system lies about 22 light-years away, close enough to study in meaningful detail. A world with 3 suns overhead, and still the possibility of gentle, temperate days. It is a quietly astonishing arrangement. Wolf 1061c is a planet of particular interest, orbiting a red dwarf star about 14 light-years from Earth, in the constellation Ophiuchus. It sits within its star's habitable zone and is believed to be a rocky world, making it one of the more compelling nearby candidates for surface conditions that might allow liquid water. Its year is short, It completes a full orbit in roughly 17.5 Earth days, circling close to its small, cool star. Scientists remain thoughtful about whether its surface conditions are truly temperate, as its orbit brings it close enough to the inner edge of the habitable zone to raise questions about a possible greenhouse effect. Still, it rests among a growing list of nearby rocky worlds worthy of deeper study. Teegarden Star is one of the smallest and faintest stars in the Sun's neighborhood, lying only about 12 light-years away, and yet it holds two planets that have drawn the careful attention of astronomers. Both worlds are close to Earth's mass, and both orbit within the habitable zone of their tiny host star, earning high scores on measures of potential Earth-likeness. The star itself is so dim that despite its proximity, it was not even discovered until 2003. That such a quiet, nearly invisible star could harbor two promising worlds is a reminder that the universe often keeps its most intriguing possibilities tucked away in plain, unhurried places. These two small planets circle their faint red sun in orbits of just a few Earth days, patient and steady in the dark. Lytton's star is a red dwarf, lying just 12.2 light-years from Earth, and orbiting within its habitable zone is a world known as Lytton B. The planet is estimated to be several times Earth's mass, placing it in the super-Earth category, and it receives an amount of stellar energy not unlike what Earth receives from the Sun. Its host star is one of the more stable red dwarfs known, showing relatively modest flare activity, a quality that makes the prospect of surface habitability somewhat more plausible. The light now leaving Lytton's star will reach Earth in just over 12 years, a span of time that feels almost reachable on a human scale. Among our nearest stellar neighbors, Lytton B is a world that astronomers hold with quiet, measured hope. Astronomers have developed a tool called the Earth Similarity Index to bring some order to the growing catalog of distant worlds. It is a numerical scale running from 0 to 1, where a score of 1 would represent a perfect match to Earth in terms of size, density, surface temperature, and other key properties. No known exoplanet has yet achieved a score of 1, but several have come reassuringly close, clustering in the range that suggests rocky temperate conditions. The index is not a measure of whether life exists, only of how Earth, like a world's physical profile, appears from a distance. It is a quiet, methodical way of asking which worlds, among the thousands we have found, most resemble the only home we have ever known. The light entering your eyes on any clear night may be traveling from one of these near matches, crossing the dark to reach you. The Milky Way is not uniformly hospitable to life. At least, that is what the concept of the galactic habitable zone gently proposes. Just as a planet must orbit its star at the right distance, a solar system may need to occupy the right region of the galaxy to give life a reasonable chance to emerge. The galactic habitable zone describes a broad, ring-shaped region, neither too close to the dense and turbulent center nor too far out in the sparse and element-poor outer reaches. Within this ring, the conditions, the density of stars, the abundance of heavy elements, the frequency of catastrophic events are thought to be most conducive to the long, slow work of planetary formation and biological development. Our own sun sits comfortably within this favored region, a detail that feels less like coincidence and more like one more quiet reason we are here at all. Near the galactic center, the conditions for life become considerably more demanding. Stars there are packed far more tightly together, and the central region is awash in intense radiation from energetic stellar remnants, supernova events, and the immense activity surrounding the galaxy's central black hole. Gravitational encounters between stars are also far more frequent in that crowded region, which could perturb the stable orbits of planets and disrupt the long, undisturbed timescales that life seems to require. A world near the galactic center might find its sky blazing with the light of countless nearby stars, a spectacular but unforgiving environment. Life, if it requires patience and stability above all else, may find the quieter, more sheltered middle distances of the galaxy to be far more welcoming. Let your body grow heavier now, sinking slowly and completely into rest. There is nowhere to go, nothing to hold, nothing at all that needs your attention tonight. Let each breath carry you a little further from the day, from its sounds, its movements, its small concerns. The stars and their distant worlds can wait for you, patient and unhurried as they always are. Feel the stillness settle around you like something warm and familiar. Your thoughts may drift, and that is perfectly fine. Let them move like clouds across a dark, windless sky, passing through without catching. You are held. You are safe. Let everything soften now and allow sleep to find you in its own quiet, unhurried way. The outer edges of the galaxy may not hold enough of the right ingredients to build worlds like ours. In those sparse, far-flung regions, the interstellar medium thins out, and the concentration of heavy elements, the materials needed to construct rocky planets with rich, layered chemistry, drops considerably. Stars, there tend to be older and simpler in composition, and the planets that form around them may be little more than bare, elemental spheres, lacking the chemical complexity that life as we understand it seems to require. The outer galaxy is not hostile so much as it is underfurnished, a vast hushed territory where the raw materials for intricate worlds simply have not yet accumulated in sufficient measure. The heavy elements essential to life, carbon, oxygen, iron, silicon, were not present at the beginning of the universe. They were forged inside stars, built up through the extraordinary pressures and temperatures at stellar cores, and then scattered outward when those stars died. Every carbon atom in a living cell, every iron atom in blood, every silicon crystal in stone was created inside a star that no longer exists. The universe had to live and die through entire stellar generations before the raw materials for complexity could accumulate. Life, in this sense, is a late and patient achievement, something the cosmos had to work toward across immeasurable stretches of time. Our own sun carries the legacy of stars that lived and perished long before it formed. Scientists describe the sun as a third-generation star, meaning the gas cloud from which it condensed had already been enriched twice over by the deaths of earlier stellar generations. Each cycle of stellar birth and death deposited heavier elements into the interstellar medium, gradually building up the chemical richness that would eventually allow a rocky, water-bearing world like Earth to take shape. The sun, and everything that orbits it, is in a very real sense the heir to an ancient lineage of stars, a quiet inheritance passed down across billions of years of cosmic history. The Milky Way contains an estimated 100 to 400 billion stars. That range alone speaks to the difficulty of counting something so vast. Even our best measurements carry an uncertainty of hundreds of billions. Stretched across a disk roughly 100,000 light-years wide, these stars are spread so thinly that most of space between them is essentially empty. And yet, gathered together, they form the luminous structure we see as a pale band arching across the night sky. Each of those points of light is a sun, a source of warmth and energy, potentially circled by worlds of its own, quietly burning in the dark. Within that immense population of stars, astronomers estimate there could be tens of billions of potentially habitable rocky planets in our galaxy alone. Tens of billions, a number so large it becomes almost meditative to hold. Even if only a tiny fraction of those worlds have developed the right conditions for life, the sheer scale of the estimate suggests the universe has had countless opportunities to try. These are not distant, theoretical abstractions, but real, solid worlds, orbiting real stars, warmed by real light. They exist right now, turning slowly in their orbits, whether or not any eye has ever looked upon them. The Drake equation is a thoughtful and elegant framework for estimating how many communicating civilizations might exist in our galaxy at any given moment. It does not produce a precise answer. It was never meant to. Instead, it lays out the chain of factors that would need to align: how many stars form, how many host planets, how many of those planets are hospitable, how often life arises, how often it becomes intelligent, and how long civilizations endure. Each factor is uncertain, and the uncertainties multiply. But the equation's quiet power lies in the way it turns an overwhelming question into a series of smaller, approachable ones, a gentle map through the unknown. The Drake equation was first written down by the astronomer Frank Drake at a small gathering known as the Green Bank Conference in 1961. That meeting, held at a radio observatory nestled in the hills of West Virginia, brought together a handful of scientists to discuss, for the first time in a serious and organized way, the possibility of life beyond Earth. Drake sketched his equation on a blackboard as a way of structuring the day's agenda. He had no idea it would become one of the most discussed formulas in the history of science, a quiet beginning for an enduring and profound conversation. The Fermi paradox poses a question that has lingered in the background of astronomy ever since the physicist Enrico Fermi first raised it informally over lunch in 1950. If the galaxy is so ancient, billions of years old and so vast, and if habitable worlds are as common as they now appear to be, then where is everyone? Even a civilization that spread through the galaxy slowly, by the standards of cosmic time, should have left some detectable trace by now. The paradox does not prove we are alone. It simply notes a silence that is, in its own quiet way, as striking as any signal we might have hoped to receive. The search for extraterrestrial intelligence, known as SETI, is the ongoing scientific effort to detect signs of technological civilizations beyond Earth. Using both radio and optical telescopes, researchers scan the skies for signals that would be difficult to explain by natural processes alone, patterns, repetitions, or narrow frequency bands that might carry the mark of an intentional transmission. It is slow, methodical, and largely unrewarded work, carried out across decades without a confirmed discovery. And yet it continues, sustained by the simple and profound recognition that if another civilization exists and has ever broadcast into the cosmos, the only way to know is to listen. On the 15th of August 1977, a volunteer astronomer reviewing data from the Big Ear Radio telescope in Ohio noticed something remarkable. A strong, narrowband radio signal had been recorded, so striking that he circled it on the printout and wrote a single word beside it: "Wow!" The signal lasted for the full 72 seconds. The telescope was able to observe it, matching the profile of what a transmission from deep space might look like. It has never been detected again, despite many careful searches. It remains unexplained, not a mystery in the alarming sense, but a quiet, enduring wonder, a single note heard once in an otherwise unbroken silence. Let your body settle now, just a little more deeply than before. Feel the weight of your shoulders release, the quiet rise and fall of your breath finding its own easy rhythm. There is nothing to hold on to tonight, nothing to figure out, nothing left to do. The universe is vast and unhurried, and it will still be there when you wake. For now, simply rest. Let your thoughts drift like slow clouds across a darkening sky, growing softer and further apart with each breath you take. Breakthrough Listen is the largest privately funded search for extraterrestrial intelligence ever undertaken, launched in 2015 with $100 million in support from the entrepreneur Yuri Milner. It uses some of the world's most powerful radio and optical telescopes to survey millions of stars, nearby galaxies, and the plane of the Milky Way for any signal that might hint at a technological origin. The program represents a quiet but determined commitment, a sustained, patient ear pressed against the fabric of the cosmos, simply and earnestly listening across the immensity of space. Breakthrough Starshot is a visionary proposal to send a fleet of tiny spacecraft, each no larger than a postage stamp, to the Alpha Centauri system using powerful ground-based lasers to accelerate them to about 20% of the speed of light. At that extraordinary velocity, the journey of 4.37 light-years would take roughly 20 years to complete. Probes would be too small to carry much, but perhaps enough to photograph a world in another star system and send back a faint signal, the first portrait of another sun's family, carried across the dark by a whisper of light. The Habitable Worlds Observatory is a next-generation space telescope concept under study by NASA, designed with one central purpose: to directly image Earth, like planets orbiting Sun, like stars. Unlike earlier telescopes that detected planets indirectly, this instrument would gather actual light from rocky worlds in habitable zones, light that has traveled across light years and carries within it the fingerprints of whatever atmosphere, ocean, or surface lies below. It would be, in essence, a machine built to take the first true portrait of a world that might, in some quiet and distant way, resemble our own. The Large Ultraviolet Optical Infrared Surveyor, known by the name LUVOIR, is another ambitious telescope concept that astronomers have proposed as a potential successor to the James Webb Space Telescope. Designed to observe across a sweeping range of wavelengths from ultraviolet to infrared, it would be large enough to study dozens of Earth-like worlds in detail, searching their atmospheres for the chemical markers of habitability or life. It has not yet been built, but the careful thought poured into its design reflects something beautiful: the human desire to look ever more clearly at the question of whether we are alone. The Habitable Exoplanet Observatory, known as HABEX, was a mission concept that paired a space telescope with a separate, flower-shaped structure called a starshade. The starshade would fly tens of thousands of kilometers ahead of the telescope and unfurl like a great dark blossom, blocking the blinding light of a distant star with extraordinary precision so that the much fainter light of any orbiting planet could be seen. The image of that paired dance in space, a delicate shield and a waiting eye, separated by vast distance and yet working in perfect concert, carries its own kind of quiet poetry. On the high Atacama Plateau in Chile, a new generation of ground-based telescopes is taking shape. The extremely large telescope, when completed, will carry a primary mirror 39 meters across, a mosaic of nearly 800 individual hexagonal segments working together as a single vast eye. It will be the largest optical telescope ever built, capable of gathering light from exoplanet atmospheres in extraordinary detail. From one of the driest, clearest places on Earth, it will reach toward the atmospheres of other worlds, reading their chemistry with a precision that was unimaginable just a generation ago. The extremely large telescope will employ a technique called adaptive optics, which corrects in real time for the constant shimmering distortion that Earth's atmosphere introduces into incoming starlight. Tiny actuators behind each mirror segment adjust hundreds of times per second, guided by sensors measuring the blur, smoothing the image back toward the crystalline clarity of space. It is a remarkable act of compensation, the telescope and the atmosphere in a continuous silent negotiation. The instrument forever gently correcting, forever reaching for a sharper and truer view of the universe beyond. Astrometry is one of the oldest techniques in astronomy, the precise and painstaking measurement of a star's position in the sky over time. When a planet orbits a star, it does not simply circle a fixed point. Both the star and the planet orbit their shared center of mass, causing the star itself to trace a tiny, repeating wobble against the background of more distant stars. By tracking that motion with extraordinary care across months and years, astronomers can infer the presence, mass, and orbital period of an unseen companion. It is a method of remarkable patience, finding worlds by the faintest trembling of their suns. The Gaia spacecraft, launched by the European Space Agency in 2013, has spent years mapping the sky with a precision that borders on the extraordinary, measuring the positions, distances, and motions of over 1 billion stars across the Milky Way. From its vantage point, far from Earth, it has built the most detailed three-dimensional map of our galaxy ever assembled. Within that vast catalog of stellar data, astronomers expect to find thousands of exoplanets revealed by the subtle gravitational tugs they exert on their host stars, worlds hidden in numbers, waiting quietly to be recognized. The light from those billion measured stars left its sources long before any of us were born. Gravitational microlensing reveals exoplanets through one of nature's most elegant coincidences. When a foreground star drifts in front of a more distant background star, the foreground star's gravity bends and magnifies the background star's light, briefly brightening it. If the foreground star carries a planet, that planet adds its own small gravitational signature, a secondary ripple in the brightening curve. Astronomers watching that subtle flicker can deduce the presence of a world they will never directly see. It is a method of extraordinary delicacy, finding planets written in passing light. There is nothing you need to hold on to right now. Let your thoughts loosen, like clouds drifting apart on a still evening. Feel the weight of your body settle a little more deeply into wherever you are resting. Your breath is slow and easy. Each exhale carries away a little more of the day. You are held. You are unhurried, and the night is long and soft around you. Simply let yourself drift, as gently and naturally as a leaf carried along a slow, dark river toward sleep. The Nancy Grace Roman Space Telescope, planned for launch in the middle of the 2020s, will carry microlensing surveys to a new level of scale and ambition. Staring toward the dense stellar fields near the heart of the Milky Way, it will monitor hundreds of millions of stars simultaneously, watching for the telltale brightening signatures of planets crossing the line of sight. Scientists expect it to reveal thousands of new worlds, including free-floating planets drifting alone through the galaxy's dark interior. It will open a window onto a population of worlds we have barely begun to imagine. Free-floating planets are among the most solitary objects in the universe, worlds that were once part of a solar system, bound to a star, circling in an orbit, but were eventually flung outward by gravitational encounters with other planets or passing stars. Unmoored from any sun, they travel through the cold darkness of interstellar space entirely alone. There are no sunrises on these worlds, no seasons, no starlight warming their surfaces. They drift in perpetual night, carrying whatever heat remains from their formation, silent wanderers between the stars. Some scientists have considered with quiet wonder whether these rogue planets might not be entirely lifeless. A world massive enough could retain a thick envelope of hydrogen gas, and that blanket of atmosphere might trap the residual warmth radiating up from the planet's interior. A gentle, internal glow left over from formation, sustained perhaps by the slow decay of radioactive elements deep within the rock. Beneath such an atmosphere, temperatures might remain above freezing indefinitely, even in the absence of any star. Life, if it exists there, would know only the warmth of the world itself. Beyond planets themselves, their moons may also deserve a place in the search for life. A large moon orbiting a gas giant that sits within a star's habitable zone would receive both the warmth of the distant star and the tidal energy generated by the gravitational pull of its massive parent planet. That combination could keep a moon's interior geologically active and its surface, or subsurface, warm enough for liquid water. Our own solar system already hints at this possibility, with Europa and Enceladus offering their quiet, icy invitations. Moons beyond our own sun may hold the same promise. Despite the compelling logic of exomoons as habitats, not a single one has yet been definitively confirmed. Tantalizing candidate signals have emerged from the data, faint hints in transit light curves suggesting something orbiting an orbiting world, but none has withstood the full weight of independent verification. The signals are real enough to be studied, intriguing enough to publish, yet elusive enough to remain unconfirmed. It is a reminder that the universe does not always yield its secrets quickly, and that patience is as essential a tool as any telescope. The exomoons are almost certainly out there. We simply have not yet held one firmly in our data. A water world is an exoplanet so thoroughly covered by ocean that no land of any kind breaks its surface. No continents, no islands, no shallow shores, only a deep and unbroken global sea stretching in every direction beneath whatever sky exists above. The oceans on such a world might be hundreds of kilometers deep, pressing down through layers of exotic high-pressure ice before reaching any rocky interior. Whether life could arise in such a place remains an open question, but Earth's own oceans remind us that water, wherever it persists in depth and stillness, tends to fill itself with living things. Planets orbiting within binary star systems, systems where two stars circle each other, experience gravitational environments of remarkable complexity. The combined and ever-shifting gravitational influence of two suns can stretch and compress a planet's orbit over time, sometimes nudging it into warmer or cooler regions of space, sometimes locking it into a stable rhythm that endures for billions of years. Whether a binary system nurtures or disrupts its planets depends on the spacing of the stars, the shape of the orbits, and the delicate balance of forces involved. For some worlds, two suns in the sky may be a blessing. For others, a slow undoing. Some planets do not orbit just one star in a binary system, but trace a wide path around both of them together, a type of orbit called circumbinary. The most famous fictional example is Tatooine from the Star Wars stories, where a desert world orbits twin suns and watches double sunsets paint the sky. That image turns out not to be purely imaginary. Real circumbinary planets have been found, drifting in wide, stable orbits around their paired stars, watching two suns rise and set across their skies. The universe, it seems, occasionally matches the visions we once thought only storytellers could conjure. Kepler 16b was the first confirmed circumbinary planet, announced in the year 2011, a world that truly orbits two suns. Detected by the Kepler Space Telescope through a precise series of transits, it circles a pair of stars locked in their own slow mutual dance. It is roughly the size of Saturn, cold and gaseous, unlikely to host life as we know it. But its confirmation mattered enormously, because it proved that the double sunset skies once imagined only in fiction are real features of the universe we inhabit. Among the elements a world must carry to support life, phosphorus holds a quiet but essential place. It forms the backbone of DNA, the molecule that carries the instructions of life, and it anchors the membranes of every living cell. Without phosphorus, those structures simply cannot be built. On Earth it cycles slowly through rocks, soils, and oceans, never abundant but always present where life needs it. A habitable world must have access to this element in some form, a subtle chemical requirement that adds yet another layer of precision to the conditions life demands. Let your thoughts slow now, like a river finding still water. There is nothing to hold on to, nothing to figure out, nothing waiting for your attention. Let your shoulders release their weight. Let your jaw soften. Let your hands rest open and easy. Each breath carries you a little further from the day, a little deeper into rest. You are held here, warmly and completely. The vast and quiet universe stretches on around you, and all of it is at peace. You can be, too. Simply drift. Nitrogen makes up nearly 78% of Earth's atmosphere, and its role is as steadying as it is invisible. By diluting the oxygen we breathe, it prevents the kind of runaway combustion that pure oxygen would bring. It also absorbs and redistributes heat, helping smooth out the extremes between day and night and season to season. Without this vast inert cushion of gas surrounding our world, Earth's climate would be far more volatile. A second Earth would need not only the right gases for breathing, but this quieter element holding everything in balance. Earth's large moon does something remarkable and largely unnoticed. It holds our planet steady, Without its gravitational steadying influence, Earth's axial tilt would wander chaotically over millions of years, swinging between extremes that would plunge continents into deep freeze or blistering heat. The Moon acts as a slow, patient anchor, keeping our tilt within a narrow range that allows for relatively stable seasons and a climate hospitable to complex life. When astronomers search for habitable worlds, the presence of a sizable moon is increasingly recognized as a meaningful piece of the puzzle. About 4.5 billion years ago, a body roughly the size of Mars, which scientists have named Theia, drifted into a catastrophic collision with a young Earth. The impact was immense, vaporizing rock and flinging enormous quantities of debris into orbit. Over thousands of years, that orbiting cloud of molten material slowly gathered itself into the moon we know today. It is a violent origin for something so serene, and yet the light that falls on you through a window on a clear night is the soft legacy of that ancient collision, still faithfully circling, still keeping the world in balance. The speed at which a planet spins shapes its entire climate from the inside out. A fast rotation drives strong winds that distribute heat efficiently across the globe. A slow rotation allows one side to bake under prolonged sunlight, while the other grows bitterly cold. Earth's roughly 24-hour day produces the familiar cycle of warming and cooling that drives our weather systems. On a world that rotates over many hundreds of Earth hours, the day-night temperature swings could be extreme enough to challenge even the most resilient forms of life. Rotation, quiet and constant, is another invisible architect of habitability. Over billions of years, a small planet orbiting close to an active star faces a gradual but relentless erosion of its atmosphere. High-energy ultraviolet and X-ray radiation from the star heats the upper layers of the atmosphere until gas molecules move fast enough to escape the planet's gravity entirely and drift away into space. This process, known as photoevaporation, can strip a thin atmosphere down to almost nothing over geological timescales. It is one reason why small rocky worlds orbiting energetic red dwarfs may struggle to hold on to the atmospheric layers that life would need to shelter beneath. Panspermia is the idea that life, or at least the molecular ingredients that allow life to begin, may not be confined to a single world, but could travel between planets carried inside rocks. When a large impact strikes a planet, it can blast surface material into space, with enough force to escape gravity entirely. That material may drift for millions of years before being captured by another world's gravity and falling to its surface. Whether living organisms could survive such a journey remains uncertain, but the transfer of organic chemistry between worlds is considered genuinely plausible by many researchers. In 1969, a meteorite fell near Murchison, Australia, and what scientists found inside it changed how we think about the origins of life. Embedded within its ancient stone were complex organic molecules, including amino acids, the very building blocks of proteins. These were not contaminants from Earth. They were formed in space billions of years ago, before our solar system even existed. The light from that ancient chemistry still echoes in every living cell on Earth today. The universe, it turns out, has been assembling the ingredients of life for a very long time, long before any planet was ready to receive them. In 1953, two scientists filled a glass flask with the gases thought to have drifted through early Earth's atmosphere: water vapor, methane, ammonia, hydrogen, and sent electrical sparks crackling through the mixture. Within days, the liquid at the bottom of the flask had turned a warm amber, rich with amino acids that had assembled themselves from nothing but simple chemistry and energy. Stanley Miller and Harold Urey had shown that the building blocks of life do not require living things to make them. They arise, almost willingly, from the raw materials the universe already provides. Far beneath the surface of the ocean, where no sunlight has ever reached, The seafloor cracks open and releases plumes of superheated, mineral-rich water into the crushing dark. Around these hydrothermal vents, entire ecosystems thrive: tube worms, translucent shrimp, ghostly pale crabs, all sustained not by the sun, but by chemical energy rising from the earth itself. These communities reminded scientists that sunlight, long assumed to be the essential engine of all life, is only one way life can find its footing. Wherever chemistry flows and energy is available, life on Earth has found a way to gather around it. Life on Earth has pressed itself into corners that once seemed utterly inhospitable. Microorganisms thrive inside boiling acidic springs, tucked into the pores of Antarctic ice, clinging to the walls of uranium mines, bathed in radiation. These extremophiles, as scientists call them, have quietly redrawn the boundaries of where biology is possible. Each new discovery of life in an extreme environment broadens the map of places in the cosmos where something similar might exist. The universe is far larger than any single set of conditions, and life, it seems, is far more inventive than we once imagined. Let your body settle a little deeper now, wherever you are resting. There is nothing to hold on to, nothing to figure out. Let your shoulders release. Let your jaw soften. Let your hands open and still. Each breath you take is slower than the last, and slower still. The thoughts of the day are already growing distant, like lights seen from a great height, fading gently into the dark. You are here, you are safe, and there is nothing left to do now but rest. Let the quiet carry you the rest of the way. Among all Earth's creatures, the tardigrade may be the most quietly remarkable. This tiny animal, no larger than a grain of sand, can curl itself into a suspended state called cryptobiosis and endure conditions that would destroy almost any other form of life. In experiments, tardigrades were carried into the vacuum of open space, aboard a spacecraft, and exposed to the full intensity of solar radiation for days. Some survived. They are not invincible, but they are astonishingly durable. Their existence whispers something hopeful, that life, once it takes hold, may be far harder to extinguish than we ever supposed. There is a thought that some scientists hold with genuine curiosity. What if life arose not once on Earth, but twice? The shadow biosphere is the idea that a second, entirely independent origin of life may have occurred on our own planet, producing organisms so different from all known life that we have simply never recognized them. They might use different chemistry, different building blocks, a different molecular language altogether. We have not found them, but absence of evidence is not evidence of absence. The possibility that two separate experiments in life could run simultaneously on the same world, side by side and undetected, is one of the quieter mysteries science still holds open. Every amino acid that life on Earth uses to build its proteins is left-handed. Every sugar in its genetic machinery is right-handed. This property, called chirality, is like a molecular handedness, and all known life follows the same rule without exception. No one fully understands why life settled on this particular arrangement rather than the mirror image. An alien biology, arising independently under different conditions, might have chosen the opposite-handedness entirely, or might mix both freely. If we ever encountered such life and tried to analyze it chemically, it might look almost familiar and yet be fundamentally, quietly different in ways that would take time to understand. Carbon is the backbone of all life on Earth, and for good reason. It forms long, stable, endlessly varied molecular chains with extraordinary ease. But silicon, the element just below carbon on the periodic table, shares some of those bonding properties. In the very cold or very exotic environments of other worlds, scientists have considered whether silicon might serve as an alternative foundation for a different kind of biochemistry. Silicon-based life would likely look nothing like anything we know, and it would face real chemical challenges. Still, the idea reminds us that carbon's dominance here may reflect the conditions of Earth, rather than a universal rule, written into the fabric of the cosmos. Water is life's great solvent here on Earth, the medium in which chemistry dissolves, mingles, and reacts. But on worlds far colder than our own, water would be locked in ice, unavailable for chemistry of any kind. Some scientists have proposed that ammonia, which remains liquid at temperatures far below water's freezing point, might serve as an alternative solvent in such environments. Ammonia-based biochemistry would be strange and slow by our standards. Operating in a frigid world we would find utterly hostile. Yet the logic is sound. Wherever a liquid medium exists that can carry dissolved chemistry, the possibility of life cannot be entirely dismissed. How life first began on Earth remains one of the deepest and most genuinely open questions in all of science. Was it in the warm, shallow pools that Darwin once imagined, where sunlight and chemistry mingled freely? Was it at the hydrothermal vents on the ocean floor, where heat and minerals drove the first reactions? Did it begin in ice, in clouds, in the pores of ancient rock? Scientists have proposed many pathways, each supported by some evidence, none yet proven beyond all doubt. The honest and rather beautiful answer is that we do not yet know, and that not knowing is not a failure. It is an invitation, still open, still waiting for the mind that will one day find the answer. The Ine world hypothesis proposes that self-replicating Ine molecules came before DNA-based life. Long before the elegant double helix existed, scientists believe a simpler molecule may have done it all, carrying information, catalyzing reactions, copying itself. RNA is remarkable in that it can act as both a blueprint and a tool, a rare dual ability that DNA alone does not possess. In the warm chemistry of an early world, these ancient molecules may have been the very first things that could be called, in any meaningful sense, alive. The last universal common ancestor of all life on Earth likely lived somewhere between 3.5 and 4 billion years ago. Every creature that has ever drawn breath, every root that has ever pushed through soil, every microbe drifting in the deep ocean, all of them trace their lineage back to a single ancient population of living cells. Scientists call this ancestor Luca, and though it left no fossil, its signature is written in the shared molecular machinery of every living thing. The light entering your eyes tonight carries the same atoms that once moved through that first, unhurried life. Microbial life dominated Earth for most of its history, suggesting that simple life may be far more common across the universe than complex life. For roughly 3 billion years, the most sophisticated inhabitants of this planet were single-celled organisms, bacteria and archaea, invisible to the naked eye, quietly reshaping the atmosphere and the oceans. Complex animals are, in the grand sweep of time, a very recent development. If the universe follows a similar pattern, then worlds teeming with microbes may be abundant, while worlds bearing creatures of any complexity might be far rarer and more precious. About 540 million years ago, something extraordinary unfolded in Earth's oceans, a relatively rapid flowering of complex multicellular life known as the Cambrian explosion. In what amounts to a brief moment in geological terms, the seas filled with creatures bearing eyes, limbs, shells, and elaborate body plans that had never existed before. The causes are still debated, but the result transformed the living world entirely. From that great blossoming, the long branching lineage of animals, including, in time, the one now resting quietly and listening to these words, would slowly emerge. There is nothing you need to hold on to right now. Let whatever thoughts remain simply drift away, like leaves carried gently down the slow river. Feel the weight of your body settling, your breathing finding its own quiet rhythm. You have traveled far tonight, across ancient oceans, through the long corridors of time, out toward the stars. Now let all of that vastness simply hold you. Soften the space behind your eyes. Let your shoulders drop. Let your hands rest open and still. You are safe, you are warm, and sleep is very close now. The development of intelligence and technological civilization may require an extraordinarily long and improbable chain of events. Consider everything that had to unfold in sequence: the right star, the right planet, the right chemistry, billions of years of stability, the emergence of complex cells, multicellular life, nervous systems, social behavior, language, and then the slow accumulation of knowledge across generations. Each step built upon the last, and any single disruption along the way might have ended the thread entirely. The existence of a civilization capable of wondering about its own origins may be, in the most literal sense, a remarkable accident. The rare Earth hypothesis suggests that the specific combination of conditions enabling complex life on our planet may be extraordinarily uncommon across the cosmos. A large stabilizing moon, a protective giant planet deflecting incoming debris, a location in a calm region of the galaxy, the right ratio of land to ocean, active plate tectonics. The list of seemingly necessary factors is long. Remove any one of them, and the story of life here might have ended quietly, long before anything with a mind could look up and ask questions. The hypothesis does not say life is impossible elsewhere, only that worlds like ours may be genuinely rare. The Great Filter hypothesis proposes that somewhere along the path from simple chemistry to a civilization spanning the stars, there lies a near-universal barrier that almost nothing survives. It may already be behind us, the improbable leap from non-life to life, or from simple to complex cells. Or it may still lie ahead, a challenge no civilization has yet found a way through. The hypothesis is not a cause for alarm. It is simply a quiet reckoning with the deep silence of the cosmos. We listen, and the universe does not answer, and we sit with that stillness and wonder what it means. The observable universe contains an estimated 2 trillion galaxies, each home to hundreds of billions of stars. 2 trillion. The number is so vast it dissolves into pure feeling, a sense of scale that the mind cannot truly hold, only gently lean against. And within each of those galaxies, orbiting each of those stars, there may be worlds. Worlds with their own skies, their own chemistry, their own long and unhurried histories. The universe is not empty. It is, in every direction, filled to the brim with the raw material of possibility. The universe is 13.8 billion years old, and that immensity of time means that life has had billions of years to arise in countless places, in countless forms, under countless skies. We are one expression of what the cosmos can do when given enough time and the right conditions. Somewhere out there, perhaps, another world turns slowly in the warmth of its own sun. Perhaps something rests there too, in the stillness of its own night, beneath its own canopy of stars. You are part of this, not separate from the universe, but woven into it, ancient and continuous and held. Rest now. Sleep well. The stars will keep their quiet watch. If even a tiny fraction of stars host habitable planets, the total number of potential second Earths becomes almost incomprehensibly large. The Milky Way alone holds hundreds of billions of stars. Multiply even 1% of those by the 2 trillion galaxies spread across the observable universe, and the resulting figure exceeds every grain of sand on every shore of our world. Each one a possibility. Each one a quiet, unhurried world turning in the warmth of its own sun, beneath its own deep and starlit sky. The search for a second Earth is, in its deepest heart, a search for our place and our meaning in an ancient and immeasurable cosmos. Every telescope pointed outward, every spectrum carefully read, every faint transit signal patiently measured. All of it is a quiet asking. We are the universe turning its attention upon itself, wondering if it has done this before, wondering if it is alone. You are part of that wondering. You always have been. Rest now, beneath your own stars. Sleep well. The The search continues, gently and without end.